Inside high-voltage power systems, transformers handle immense loads of energy. When faults occur, the stakes are measured in millions of dollars and grid-wide blackouts. While electrical and thermal issues can be mitigated, mechanical defects are far more persistent. During short-circuit events, electromagnetic forces spike to levels 100 to 900 times greater than normal load conditions, tearing at the internal structure of the transformer. This extreme force frequently pushes the disk-type high-voltage windings out of their vertical, axial alignment with the surrounding layer-type low-voltage windings. This schematic illustrates the mechanical fault. The variable delta H represents the axial displacement of the high-voltage winding against the low-voltage winding. Because this damage is structural, standard monitoring systems miss it. The displacement sits silently inside until complete failure. Preventing catastrophic grid failure requires a method to measure this hidden physical displacement while the transformer remains online and fully operational. Historically, engineers measured short-circuit impedance. Variances over 3% signaled serious problems, but this required shutting transformers down. The modern solution is online monitoring using transfer function analysis. This method maps the active transformer as a complex linear system. For a standard 1.6 MVA unit, the mathematical map resolves into a 16th-order system. The diagnostic challenge is isolating a single metric within this massive transfer function that is highly sensitive to physical shifting and scales predictably as the damage gets worse. To automate this diagnosis, the algorithm requires a signal metric that scales monotonically with the severity of the fault. It must avoid false positives and prevent severity miscalculations. This is the RLC circuit diagram showing the equivalent mathematical model of a healthy transformer, detailing the connection between high voltage and low voltage windings. Notice the components representing the coupling between the two winding blocks, the mutual inductance, labeled MIJ, and the capacitance, labeled CHL. When axial displacement occurs, the physical gap between the windings changes. That physical movement directly alters the mathematical values of the mutual inductance and the capacitance. Because these components bridge the two halves of the system, a localized change here reshapes the behavior of the entire equivalent circuit. As the circuit parameters fluctuate, the mathematical poles and zeros of our 16th-order transfer function shift in response. We can stress test this shifting model across 4 distinct fault conditions, simulating axial displacements of 15, 30, 45, and 60 millimeters. The resulting mathematical models tell us exactly how the damaged transformer will alter injective signals. That gives us the raw data needed to test both time and frequency domain metrics for reliability. We evaluate the frequency domain first, as it is the most common diagnostic testing ground for linear systems. This Figure 9 Bode diagram plots the frequency response for the healthy transformer against all 4 displaced conditions. Pay attention to the high frequency range, between 10 to the 5th and 10 to the 7th radians per second, where the resonances are concentrated. At the first local maximum around 236 decibels, the lines overlap tightly, showing only fractions of a percent variation. However, examining the low-frequency behavior around 100 radians per second reveals a completely different picture, showing distinct, readable separation in signal magnitude. The raw sensitivity is immense. At the maximum physical displacement of 60 millimeters, the signal magnitude drops by 22.07%. But the viability of a metric depends on its scaling progression. Watch what happens to the magnitude data as the displacement increases from 15 millimeters to 60 millimeters. At 15 millimeters, the drop is 7.59%, but at 30 millimeters, the drop shrinks to 6.9%. At 45 millimeters, it shrinks again to just 1.38%, before plummeting to 22.07% at the 60 millimeter mark. This behavior is mathematically non-monotonic. The signal data does not track sequentially with the physical reality of the growing defect. This makes the Bode plot dangerous for automated diagnostics. An algorithm reading these signals could easily flag a minor 15 millimeter fault as an emergency, while ignoring a much more severe 45 millimeter shift. Shifting to the time domain, we begin with the Figure 8 impulse response plot. Because settling times across all fault conditions are nearly identical, our analysis focuses entirely on the peak amplitudes at the very first extrema. the impulse response achieves the highest raw sensitivity of any tested metric. A 30mm displacement registers a massive 31.33% change in amplitude, but mapping the progression reveals the exact same flaw we saw in the frequency domain. The amplitude variations bounce from negative 7.23% up to positive 31.33%, down to 22.89%, and back up to 26.63%. Its extreme sensitivity is rendered completely useless by its non-monotonic variation. An automated system simply cannot parse this data reliably. This leaves the final metric under evaluation, the step response of the system. This is the Figure 7 plot comparing the healthy baseline to the 4 displacement levels. Dismissing the identical settling times, we isolate the amplitude of the first extrema. The raw sensitivity holds up to scrutiny. A 60mm displacement yields a highly detectable 21.24% change in amplitude compared to the baseline. Examining the incremental progression of these variations shows how the metric responds to worsening conditions. The values move from negative 2.65% to positive 2.65%, to 16.81%, and finally to 21.24%. When tracking the variation, the data scales directionally and predictably. As the fault physically worsens, the percentage change travels continuously in a single direction. This is monotonic scaling. The step response's first extrema offers the exact mathematical balance required: sensitivity high enough to detect minor faults, and strict monotonicity to allow an algorithm to perfectly track the severity of the damage. A robust online diagnostic monitoring system cannot function on guesswork. It requires data that plots logically. Plotting the frequency and impulse response data streams results in unpredictable zigzags. The values jump up and down, completely divorced from the physical reality of the shifting coils. Plotting the step response data stream, however, draws a clean, continuous upward curve. Frequency and impulse analysis offer impressive, highly sensitive data points. But only the step response translates physical reality into reliable algorithmic logic. The engineering recommendation is clear. Automated diagnostic systems should monitor the peak amplitude of the step response at its first extremum to track axial displacement online. Naturally, this mathematical proof operates within the strict boundaries of system linearity. Real-world deployment must account for external variables not modeled in this baseline simulation, most notably the baseline shifts caused by operating temperature fluctuations inside the transformer. Filtering out that thermal drift is the next hurdle in refining these algorithms. But the core logic holds. By mastering the step response, engineers can keep transformers online, accurately monitor their mechanical degradation in real time, and catch catastrophic grid failures long before